Hello guys, welcome to this video, which is about my strobe tuner. So this is a guitar tuner which uses the strobe principle. I have some LEDs here that show the strobe signal. And in this video I want to talk a little bit about what is a strobe tuner, how does it work, about the history of strobe tuners. And we want to look a little bit into some schematics and also some program code. Obviously, you can see a microcontroller board in here. So we're using some program code as well. Although I have to say this is not microcontroller based, and I will come into this detail very soon. So let's have a look what components or what parts we have in the strobe tuner. So here is the battery inside of this little battery compartment on the right side. Then here is a switch to switch it on and off. Then we have a switch to select the string that we want to tune to. It has 6 positions for the 6 strings of the guitar. Then in here, installed vertically, you can see the microphone amplifier. It is a very simple design using just one transistor. Then here is the electret condenser microphone capsule. Then of course here we have the display board, which has the LED. It's an 8 LED band. Here we have an IC, that is a digital IC, it's a ring counter. Then in here we have some trimmer to set the bias. And here is a switching transistor. And then there is the microcontroller board. I'm using an Arduino Nano here. And as I said, the project is not based on the microcontroller. I used the microcontroller as a reference oscillator, so you could also build other forms of reference oscillators, including fully analog designs that would work exactly the same. Now, before we look a little bit more into the history of strobe tuners and into schematics, I should probably give you a demonstration on how this device works. So I'm sitting here with my guitar. It's not really very badly out of tune. I've tuned it yesterday, but we will see it's very slightly out of tune. And I start by tuning the lowest E string. I have set the switch here to the 12 o'clock position. This is where we have the lowest E string. And on the LED band here, we will see an LED pattern, and it will have 3 possible positions. It can move to the left, which will indicate that the string is tuned too low. It can move to the right, which will indicate the string is tuned too high. Or it can be a standing pattern, which indicates that the string is tuned correctly. And of course, our goal is to get a standing pattern on the LED display, which will then indicate we have tuned the string correctly. Let's start with the low E string. So as you can see, the LEDs are drifting very slightly to the left. I will now tune a little sharp. The movement is getting slower. It's getting even slower. Very slight drift to the left. Still very slight drift. And I would say about here is where we have a standing pattern. As you were able to see, it's a very sensitive indicator. You were almost hearing no change in pitch, only very slight changes in pitch, which I did. That led to a different indicator, different display. So let's use the A string now. I have already adjusted the switch to the A string. Only a very slight drift to the left, so I'm tuning up a little bit. Maybe like so. I think it's almost drifting a little bit to the right now. Like so. Let's use the D string, drifting to the left, indicating too low. Now it's drifting to the right. I was tuning to high. Maybe like so. Now the G string. That is very much too low. A little bit too high now. Maybe like so. The B string. Also too low. Maybe like so. And as last string, the high E string. Maybe like so. Now let's give the guitar a try. We can hear if it's tuned correctly. E major chord, C major chord. I think it sounds pretty clean. So this is it for the demonstration. I think you were able to see that this is a handy little device. It still has some weakness. Maybe on the high E string you were able to see that I was not able to get a very good picture here on the LED display very long into the sustain phase of the sound. So I'm thinking about adding a little bit of automatic gain control here on the microphone amplifier so I can use a longer sustain phase of the sound. But this is just the way like these projects evolve, and at this point it is pretty much finished. I have it in this little box. I can use it, I can give it tests, and I can still continue to improve it a little bit. Okay, now let's look a little bit into the history of strobe tuners. So here I found a very interesting website that explains the model ST6, the Strobe Tuner ST6 by the Con Corporation. And the Con Corporation was one of the first companies building a strobe tuner. Now this is not the very first one that they built. The strobe tuner was invented in the 1930s, so almost 100 years ago. And it has strong connection to the development of radio electronics technology, because we will see in the schematics that we need vacuum tubes to build such a device. It is very important to understand that the device is an electromechanical tuning device, and it does not require any microcomputers or any software to run. So it was in the pre-computer era when these machines were invented and used. So at the end of this document here, we will see the schematic. Here is a strobe disc that is built into such a strobe tuner. And you may recognize this from record players. Some record players also have this on the platters, so you can fine adjust the speed. This is the same principle. And we are interested in the schematic. Now this is not a very good scan. Also here in this document they apologize for the quality of the scan, and so do I. I didn't find a better one, but it's good enough for us to see the main sections of such a strobe tuner, because my strobe tuner, and I would say pretty much any strobe tuner, uses pretty much the same principle, although we may use completely different components to achieve that. So what do we have here? I would like to explain 4 different sections. Now here on the right side, on the bottom part, we have the power supply. Here they are using mains power. My strobe tuner uses a battery. All modern implementations can run on batteries, of course, no problem whatsoever. Then we have here a microphone amplifier. It says input jack here. You may be able to read that. So here you can feed in a signal. There's some sort of volume control. And then we have basically a tube as a microphone amplifier. And then we have a driver tube, and the driver tube, then the output drives 2 neon lamps Here, maybe you can read it, neon lamps. It's written here. And these neon lamps, they will then shine light onto the strobe disc, which we have here. The strobe disc will be rotating the whole time, and then the neon lamps will shine light on it, and the light will be modulated with whatever audio frequencies we put onto the input jack of the microphone amplifier input. So basically, a very simple way of describing is this light will flicker. This will not be very obvious to human eyes, of course, but it will flicker with the modulation of the input signal. So now let's move on to this section here. Here you can see we have a huge inductor and we have switches to select. And we will use, depending on where the switch is set, we will use only a portion of the inductor. We will not use the full inductor, the whole size. And also you can see a portion of this inductor is variable, so you can adjust it. We will need that to have a fine adjustment of the frequency that we want to tune. Keep in mind, not all instruments are tuned to A440. Some will be tuned a little higher or a little lower, so we need some sort of fine adjustment. I did not include any form of fine adjustment into my tuner. My tuner will always tune to A440. So this inductor, together with the circuitry on this side of this double triode tube, will then form an LC oscillator, L because of the coil and C because of the capacitors that we use. And this will be the reference oscillator. And on this part of the document here, this is the fourth section, you will pretty much see a push-pull amplifier driving this output transformer, and then at the output of the transformer we will drive a motor with the signal. And the second part of this tube is then the phase splitter that you can see in every push-pull amplifier. So this is basically how this works. So to give real simple names, we have an oscillator, reference oscillator. We have a driver stage with a motor. We have a microphone amplifier with lamps. And we have a power supply. So let's make a little drawing. We can have an overview how the circuit works. So we have an oscillator. Okay, I will leave out all the unnecessary stuff like the switch for different frequencies. You can build a strobe tuner for just one frequency, then you don't need a switch. Of course, it would not have much value to use such a device. And then the oscillator will have a connection to a motor driver. So we have a motor driver, and then we will have spinning disc. Let's write SP for spinning disc. Then here we will have neon lamp. Neon lamp. Then here we'll have a microphone input. And we will have a microphone amplifier. And the microphone amplifier will also have some driver. In the case of neon lamps, in the case of LEDs, it will not be very difficult to drive them. And the driver will drive the neon lamp. And then the neon lamp will shine light onto the strobe disc. That's the basic overview. And we can now compare this to my implementation of the circuit using no moving parts, only electronic components. So this is the original schematic that I found somewhere in the internet a couple of years ago. And this is where I based my design on From the original circuit, I didn't keep much except for the ring counter. And the ring counter is the very basic circuit here for the strobe tuner. So the CD4022 is an 8-bit ring counter, and it does exactly what it says it does. So it counts each of these output to high in consecutive order. And then when we have reached the last output, when this has turned high, then we will reset to the first one. And the counting will take place whenever we will get a TTL signal, a positive edge, going into this input here, pin number 14. And as you can see, for these LEDs to be lit, we have a second condition which must be met, and we need this transistor to close. So only when this transistor is closed, there is a connection between emitter and collector, only then the current can flow to the ground. And in order to close this transistor, we need a high signal coming from this side of the circuit. So basically there's two sides of the circuit, and this may already remind you of the original strobe circuit which we have seen, which also consists of a reference oscillator and a microphone amplifier, and we pretty much have the same here, except that they do not show the part of the reference oscillator. They only show the input for a reference frequency, so they will leave it to us to generate the reference frequencies. But other than that, we have two input channels which are exactly the same. Look at this part of the circuit until here. So these two are completely matching. And here you can see there is an electret condenser microphone. So they assume that you will put your microphone input into this part of the section. Now let's come to this here. These ICs are flip-flops, and the way they are designed here, the way they are put into circuit here, is they act as dividers. And with this switch, they will let us decide whether we want a division by 2, which is when we will use these two lines, or if we want a division by 4, which is when we will use this line divided by 2 and then another divided by 2. And I have simplified this. I will come to this in a second. So let's talk about this part of the circuit here. You may also recognize that this is a digital IC as well, and it may be looking a little bit odd that this is used on an analog signal. Here it's clear when you connect the microphone here that this is used on an analog signal, but the CD4069 is a hex inverter, but it can also be used as amplifier or for filter, and you would then have a very high impedance resistor switched from output to input, basically powering the input at half the supply voltage, and then this acts as an amplifier stage. And in this setting here, this acts as a trigger. So what we're basically doing here with this circuit is we're transforming our sine wave, or I should say sinusoidal wave, because musical instruments do not produce real clean sine waves, but are composed of multiple sine waves. And then we will trigger this to TTL level. So we have TTL signal here and also a TTL signal here. So what I did keep was the transistor, and I left the trigger circuit because you can actually use, if you use a MOSFET and you use some properties of LEDs, and one of the very important properties of these LEDs is that they have a very high brightness even if the transistor is only partially on. And you can then simply use a voltage divider here to set some current so that the LEDs are barely off, and then you can even use a sinusoidal signal which you take from this point here, from the transistor, to drive this transistor or I use 2N7000 NFET. So you only need a little bit of extra voltage to turn this on enough so that these LEDs will light. And also for the divider circuit here, division by 2 or division by 4, I left it out because what we are interested is the frequency ratio from here to here, of having a frequency ratio of 1:2 or 1:4. And we can achieve exactly the same if for the reference frequency we only will provide twice the frequency that we want to measure here, or 4 times the frequency that we want to measure here. This will create exactly the same ratio as using dividers. So we can save these components simply by building a different reference oscillator that has 4 times the frequency that we want to tune. So as an example, if you want to tune the A string of the guitar that is 110 Hertz, you would have to feed in a signal of 440 Hertz here as a reference signal. Okay, so yeah, I also figured out this has an advantage because when we use the lowest E string of the guitar that has around 82 Hertz, I didn't keep the decimal places in my mind, and then we divide it by 4, we're getting a pretty slow signal already here, and then we can already see some flicker on the LEDs. So I think my approach is even a little better than what they have done here. So let's do a little more drawing. This is my implementation for the LED strobe. So I'm using a reference oscillator. That is an Arduino Nano, in my case. Then I have a switch with a couple of positions. Let's simply write switch. Okay. Then I'm feeding this directly to the CD22 ring counter. That is connected to the LED band of 8 LEDs. And then we will have a FET that is a 2N7000. And in here, we will then have a voltage divider. One side goes to 5 volt, the other side goes to ground. And in here we will have a coupling capacitor. And now we can go to the microphone input. So I'm using an electrode capsule. Then we have a microphone amp. That is 1 transistor. Very standard configuration, small signal amplifier. And then we use the output and we couple the signal into the gate. And the bias is set, as I've already explained, so that you barely switching these LEDs off. In fact, when I use the tuner in a very dark environment, like in the evenings in the room, I can barely see them glowing. And then you only need a little bit of voltage. So in here you will have the sine waves. Okay. And you only need a little bit above this level here, and then we will couple the AC signal into the voltage that is already present here, and this will turn on this transistor enough to make the LEDs fully light up. So if you compare this to the older design, you can see that there is really a lot of similarities. So the older design has a reference oscillator. They used an LC oscillator. Here we're using an Arduino as a reference oscillator. Then the ring counter is basically the same as the motor driver and the spinning disc. So because the ring counter does exactly that, it is the spinning element, the spinning LEDs. And then the neon lamp driven by the mic input is the same as this transistor being switched in the rhythm of the signal. So we're using this signal here to turn the transistor on and off. That also creates the modulation. So this is how you can transform this older design into something newer that doesn't need any moving components. It's very simple, very easy to build. Now, as a next step, let's have a look at the program code so you can understand what the Arduino Nano does, and it's not very complicated. So here you can see the program code. It's not a huge program, very short program. Let's go through it. I always like to leave a lot of comments in the program, because once you have stopped working on the project, if you return back to the project after a couple of weeks or months, it will then oftentimes be difficult to understand what you did. So here I write the registers for the timer. These are the registers that we have to set in order to get the timer running in the way that we want it. And then also for the timer, you will have a prescaler. So I have wrote down the values for the prescaler, and I wrote down the values that I have to preset the timer. So it will then count down from this value. And I also made some calculations about the precision of the frequencies. So here are the ideal frequencies that I want to tune. So all the frequencies have to be multiplied by 8. Keep in mind, in the original circuit, there was a frequency divider by 4 or by 2. And to get one full cycle, this is like with a blinking LED. If you want to have 1 second blinking pattern, you have to set 500 milliseconds. So in order to get 1 second, you have to use 500 milliseconds times 2, because this is then one full cycle. So in the reality, we have to multiply everything by 8 here for this circuit if we want a division by 4 at the ring counter. And then when you use timer, there's one problem, and this is also part of the learning curve, that you learn what a timer can do, what it cannot do, and then you can do some research that there may be better and more effective ways of implementing a very precise reference oscillator. And the best way to do it is probably by using DDS, Digital Direct Synthesis, and I'm going to try this in the future. But for now, this is not really bad. You can have a look here. So let's take the A string. The A string has a frequency of 110 Hertz. Then we have to multiply this by 8. This is then 880 Hertz. And then here are the settings for the timer. And then we will get 879.991 Hertz. So this is an error of 0.009 Hertz. So we're getting really close. Still, it can be done a little better. It is what it is. For now, this works. So then here we have some pins that we want to use. It's always nice to use these define compiler directives, so you can use more descriptive explanation, as W pin is the switching pin and AN pin is the analog pin. So I have a 6-position switch, and I use voltage dividers on the switch. so I can then see to which position the switch is selected. And then let's go to the main part. The main part will be the ISR, or ISR is short for interrupt service routine. So this is here. And you have to give a definition of what event you want the ISR, the interrupt service routine, to trigger. And we are using the timer 1 compare. And what this means, we are setting a timer with some predefined values, and then the timer will count down. And whenever it reaches to 0, it will have a timer event, and then we'll call this interrupt service routine, which will interrupt whatever code we are executing at this time, and will then execute the code here inside of the interrupt routine. You have to use very short code only. And what we're doing here is we simply change the pin. So this could even be done in a faster way by accessing the registers directly, but for the very low frequencies that we're using here, this is fine. So we're inverting the switch state, and then we're setting the pin to the new switch state. So in other words, in simple words, if the switch state was on, we will then set it to off, and then we write the switch pin to the off state. And if it was off, we will then set it to on, and then we will write it to here. So this is what creates the reference frequency. And in the main loop, we pretty much the only thing we do, let's look at the while true. This is where the real main loop starts. This code is from the development stages. So this will be executed only once. And then we execute the code that is in here that will be executed eternally. So whatever value we see at the analog input, we will then check for certain values here, and then we will simply set the timer registers to the values that we need in order to generate the frequencies that we want to have. And only if the analog value changes, and this means we will reset the timer to another value, and then we will have a different output frequency created by our interrupt service routine over here. So this is pretty much everything here in the code. I'm going through it again very slowly, so you can make screenshots if you want to. And this is all you need in order to make you a reference oscillator for your Strobe Guitar Tuner. So I'm pretty much through with the content that I wanted to show you here concerning my little Strobe Tuner. Maybe let's do some wrap up. What are the pros and cons of using or building such a Strobe Tuner? Of course, building is always fun. Now, the pros, I would say, the display is very sensitive. You have seen this in my demonstration, that you can show a real effect on the strobe display when there is almost no audible effect in the change of pitch. So it will be very easy to get the string tuned very precisely to the reference frequency. The tuner is not based on an algorithm. I have shown you I use the microcontroller only as a reference oscillator. It doesn't do any processing of audio, so there is no delay. It's a very, very fast tuning device. It directly reacts on the sound signal because we are using the sound waves directly, and the operating principle is a frequency comparison. So it's no calculations are done here. That's a difference to most other tuning devices. And the display and the not the display, but the working principle is pretty much related to, maybe you know, Lissajous figures from the oscilloscope. This is also a frequency comparison, and we do pretty much the same here. One of the cons maybe, well, you have to get used to the display. It's different form of displaying the information. And the display may not be as helpful when when the pitch is very far off. But this may also be a problem with other tuning devices. Then the tuning devices will show information which are not really helpful. I was thinking about maybe adding a small loudspeaker. You could, of course, use the sound that the reference oscillator produces to drive a speaker. So this might give you an indication of in which direction you have to tune the string. So maybe this would make a nice addition. Okay, maybe some words about improvements. Of course, I have to clean up here the cables a little bit. They are a little bit too long still from the construction phase. And then two things that I want to change. The microphone amplifier here, I want to give it a little more amplification and maybe add a little bit of automatic gain control, so I can have a reading here on the display longer into the sustain phase of the note. And then, of course, I want to change the reference oscillator, and I want to use DDS principles, which means we basically run the interrupt service routine at a very fast frequency and count up a phase accumulator, and then we have much finer resolution with the frequencies. But it's only a minor improvement, because already now we are very well in the range of tolerance that we can accept for tuning a guitar. So maybe a little bit of outlook. I will have more tuning devices. I'm also building other tuning devices, and I also want to make a full tutorial about electronic tuning devices, so you can understand a little bit more about what type of signals do we look at, how do we derive the frequencies that we want to tune, how can we measure frequencies, which algorithms can we use. And it will be tuning devices that use sampling technology. It will be some simple like I've shown you here. And there's also, I plan to build a fully analog tuning device using an analog reference oscillator with NE555, the famous 555 chip, and using an analog scale to show the deviation of the tuning. So this is for the future. But for now, this is it. I hope you enjoyed this video. If so, please come back anytime you want. You will find more videos like this here on my channel. Bye for now.